Hello, everyone. You are listening to Uncomfortable Truths with Euclid Phoenix, where I talk about politics, religion, and other BS that I find interesting. Today, for BS, we are going to talk about dark matter and dark energy. What we understand so far. The term dark matter refers to some form of mass or mass effect in the universe that does not emit or absorb light, or more precisely, electromagnetic radiation in any significant amount, hence dark. The evidence for it is strong. For instance, galaxies rotate in such a way that unless there is extra unseen mass, stars at the outskirts would fly off, but they don't. Colliding galaxy clusters such as the famous bullet cluster show that most of the mass doesn't behave like normal gas. In the collision, the hot gas flows, but the gravitational mass, inferred via lensing, doesn't follow the gas, pointing to a non-interacting mass component. In cosmological models, the standard CDM model, dark matter makes up roughly 27% of the universe energy mass budget. Ordinary visible matter, 5%, dark energy, 68%. The leading candidate explanations are particles beyond the standard model of particle physics. For example, weakly interacting massive particles, WIMPs, axions, or other exotic forms, extra dimensions, primordial black holes, or modifications of gravity. Dark energy is the name given to whatever is driving the accelerating expansion of the universe. In 1998, two independent teams found that distant type supernova were fainter than expected, implying the expansion of the universe is speeding up. It acts in the simplest model like a form of energy inherent to space itself, a cosmological constant, and Epstein's equations giving rise to a negative pressure that drives the expansion. In current cosmic energy budget terms, dark energy makes up 68% of the universe, dominating the large-scale fate of the cosmos. What we still don't know and why it matters. This is where things get juicy. There are more unknowns than knowns. As a writer, this is exactly where the imagination strays into wonder. But in science, it's where new discoveries await. What is dark matter? Fundamental identity. We don't know for sure what particle or entity dark matter is. Is it a WIMP, an axion, a sterile neutrino, a primordial black hole, or something else entirely? Despite many decades of searching, direct detection of dark matter particles, i.e. seeing them interact non-gravitationally, has not happened, or at least nothing definitive. There are puzzles in the small-scale structure of galaxies, e.g. the core cusp problem. Observed dark matter density profiles in dwarf galaxies are shallower than predicted, and the too big to fail and missing satellites problem. Some new theories propose self-interacting dark matter, SIDM, a dark matter type that interacts with itself, but not much with ordinary matter. This could help with some of the small-scale structure issues. And still, what if dark matter isn't a particle at all, but a breakdown of our gravity theories at large scales? modified Newton dynamics, MOND, or emergent gravity proposals challenge the usual interpretation. Why this matters. The identity of dark matter is crucial not just for cosmology, but for practice particle physics, which lies beyond the standard model. For galaxy formation, how structure emerges, and maybe for new physics entirely. If you're writing fiction in a specific cosmic vein, the fact that 85% of matter is unseen is an invitation. What is dark energy and its constraint? Is dark energy simply the cosmological constant, a fixed energy density of empty space, or is it something more dynamic, e.g., quintessence, evolving scalar field, and with changing strength over time? Recent observations hint that dark energy might weaken or evolve over time, e.g., new surveys suggested that the strength of dark energy may not be truly constant. What drives dark energy? Why the observed magnitude? There's a why so small but not zero problem. The theoretical predictions of vacuum energy yield absurdly large numbers, but observations show a small but non-zero value. Is dark energy and dark matter connected? Some theories propose coupling or interaction between them. The darker sector. If yes, what form does that interaction take, and why is it tuned the way it is? Why this matters. The nature of dark energy determines the fate of the universe. Will expand, continue accelerating forever, leading to a big freeze or big rip, slow down, reverse, or modify in unknown ways. As we refine our measurements, we might uncover entirely new physics. For a speculative fiction writer, the wind of expansion becomes a storyline, a metaphor, a cosmic tide, maybe even a character. Why the numbers work out the way they do? Coincidence problem. It's curious that we live in a time when dark energy, dark matter, and ordinary matter are of comparable magnitudes on the scale of energy density parameters, even though they evolve differently over time. Why now? This cosmic coincidence is puzzling. Why do the observed proportions, -5% ordinary matter, or not -5, 5% ordinary matter, 27% dark matter, 68% dark energy, work out so neatly in the standard model? Any shift would change the structure formation history drastically. How do dark matter and dark energy influence structure formation and evolution? We know dark matter acts as the scaffolding for galaxy formation. It clumps, forms halos, ordinary matter falls in. But exactly how dark matter behaved in the early universe, how it clustered at very small scales, how it interacted, if at all, with itself or other fields, is still uncertain. For dark energy, measurements of the growth of structure, galaxy clusters, cosmic web, show some tension with the predictions of the simplest CDM model. For example, a recent study found that the growth of cosmic structures is suppressed more than predicted, suggesting a new dark sector physics or modified gravity. Could our assumptions about gravity be wrong? One radical possibility, perhaps what we call dark matter or dark energy, is rarely a sign that our laws of gravity, e.g., general relativity break down on cosmological scales? If so, the dark components are mirages. For example, modifications to Newtonian dynamics, MOND, or emergent gravity frameworks. While these have trouble explaining all the data, they remain in the conversation. What is the ultimate fate of the universe? If dark energy is constant and dominates forever, the universe will keep expanding. Galaxies will recede, stars will burn out, and we approach a heat death, big freeze. If dark energy grows stronger, phantom energy, it could lead to a big rip where even atoms are torn apart. If it weakens or reverses, perhaps expansion might slow or reverse, leading to a big crunch or bounce. Recent observational hints of weakening dark energy make this more than mere speculation. Thank you for listening to this podcast. Please subscribe to it and feel free to visit my website in the notes for the show.